Okay, so let's start. Again, a couple of important announcements. So one is registration. So as far as I know, can you hear me well at the back? 24 people got from the waiting list, got in. So you should have received messages from Holly. Who got messages from Holly? Okay, most of you are not here. If you or your friend did get a message, so my understanding is that undergrads should go to the academic office because they have to complete a form there. Graduate students that got a message from Holly should get my signature as of this week. So come after class or come in the evening to get my signature. Otherwise, you won't be able to register, and I will not be here next week, which brings me to this part of it. So you definitely want to do it now. And if you do want to register, do it as quickly as possible because we want to know what's the status. There are still a couple of slots that are open. I assume that in the next week there'll be a few others that are open or that become open. So, but I want to, once you get a message, I want to move quickly so that we know exactly what the status is. Questions on this? Today we have another lecture. In addition to this one, there's another lecture in the evening, same place here, 7 o'clock. I apologize for the late time. You know, that's really the only time we can do it without too many conflicts. Hopefully it's not too late for most of you. The reason is that I will be away next week, and I don't want to miss lecture. So it's going to be one late lecture this week and another late lecture in 2 weeks. So we'll have 3 lectures in 2 weeks also. Questions on this, on the homework? No questions. Excellent. Okay, so let's move on. So this is where we were last time. I'm just kind of summarizing. We talked about what is learning. We talked about, we gave an example of one learning algorithm, one key, very important learning algorithm that learns linear functions. And we discussed all these issues. You know, what does it mean? What function do we want to learn? What does it mean to be best? And how to find this best function under some definitions. And all these essentially are on these slides, all these definitions. So now we want to move on and see, okay, so what is left? So there's a lot of other questions that we didn't even touch on. So one is that I kind of convince you that it's okay to learn linear functions, but we really want to address this question of what else can be done, even though eventually most of the class we are going to learn linear functions. Of course, there's another set of questions that have to do with being able to say something about the quality of what we're learning, the complexity of what we're learning that we didn't touch upon at all. So we're going to leave question 2 to later, and we're going to start addressing question 1 today. So the key conceptual observation that we want to make in moving from last time to today is that before we actually decoupled 2 important steps in learning. The notion of the feature space, the generation of the feature space, and the learning. And we said that, you know, we're going to deal with the generation of the feature space. If needed, we're going to make it more expressive. And once we have it, we're going to learn a linear function. Today, and this is kind of the picture that or the cartoon that you want to keep in mind when you think about this ability of enriching the feature space so that what you learn eventually is expressive enough. When we deal with decision trees, we don't need to do this. And this is what we're going to start doing and hopefully finish doing today. So the idea is that the algorithm is going to deal with the original feature space and handle the transformation itself. So again, you can think about the Badges problem. When we played with few feature spaces, you're going to play with it again in the next problem set. And another perspective that I mentioned last time and will mention again today is one other significance of decision trees is that if you really think about a generic learning algorithm, you don't know a lot about the application area, the task, the type of data you're going to see, the dimensionality, and so on, and you need a learning algorithm, you need to know decision trees. Because the generic learning algorithm that I would recommend, and many would recommend, would be to learn a bunch of decision trees, a large number of decision trees, and then combine them together with a linear function, and there are multiple ways of doing it. And we're going to talk about it. Okay, so today I'm going to talk about decision trees, basically nonlinear classifiers, give a learning algorithm, and talk a little bit about overfitting issues that are interesting in the context of decision trees. They're interesting in the context of anything else we're going to do later in the class, but this would be a good place to introduce it. Okay, so when we think about decision trees, a good thing to think about is how do we want to represent data? Because at the bottom line is that decision tree is a way to represent a lot of data in a compact, easy to read, easy to use data. So let's think about other ways of representing data. So here's a simple way. We have a large table. We have n attributes. I'm going to use interchangeably the word attributes and the word features. And assume that you want to know something about people that are represented as entries in this table. So some of the entries would be, for example, features of people, and you want to know whether they own an expensive car or not. So the simplest way would be to build some kind of a histogram, let's say, on the first attribute, own an expensive car or not. So I have blue is the number of people that own, maybe the other part of the histogram, those that do not. This gives me some information. I want to split it on some other attributes, for example, gender. So now I have two attributes, and my histogram is going to be like this. Right? So gender and own, female and doesn't own, male and own, male and doesn't own. So now I have, but what's going to happen if the number of attributes grows? 16 attributes or more. So if I want to do just the 1D histogram, the one that I show here, only 60 numbers, not so bad. But if I want to do 2D histograms, already 16 choose 2, right? I have to look at all pairs. If I have 3D, hundreds of, and of course, once I have 100 attributes, it becomes already infeasible, right? So if I have 100 attribute, just 3D tables, so I'm just looking at subsets of 3, 100 choose 3, it's easy to think about that it has to be this order of magnitude, right? So it's 10 to the 2, cube, it's 1,000,000, divided by 6, you get about 160,000. Way too many, and we don't want to deal with it this way. So we really need a better way to represent the data. And specifically, we want to know, okay, so what attributes do we want to look at first? Because they're more meaningful. And the question is how to do it. And information theory is going to help us in thinking about this, and this is going to be the key algorithmic component that we're going to deal with when we learn decision trees. Okay, so decision trees really is going to be a way to represent data, or a data structure if you want, that is hierarchical, can be used as a non-parametric classification. Basically, what I mean here is that I don't make any assumption on how to parameterize this model, right? So just a keyword here. And we can use it both for classification and for regression. We're going to talk about classification when we present the algorithm. So the goal is going to be, you're going to give me a set of examples. my goal is going to be to learn a decision tree that represents the data well, and we're going to think about what does this mean. So eventually, once we've learned this representation, we're going to use it to classify new examples. So here's an example of a set of examples that you might see. So these are 3 classes. The labels are A, B, and C, and what you see is some geometric shapes that you can characterize perhaps by the color and the shape. And I want to represent this set of examples in a better way. So you can think about, okay, so I'm going to condition on shape and color, and I'm going to figure out what is the label as a function of shape and color. The nodes are going to be the test for the feature value. In this case, what is the color? What is the shape? And then I'm going to branch on these nodes. Eventually, I'm going to get to leaves, which will specify the label. So this allows me, eventually, once I have this representation, also to classify instances into these disjoint categories. So for example, here, and there are 2 computational problems, of course, once you have this. One is to evaluate a decision tree. That is, given an example, go down the tree to get to the appropriate label. For example, if you have something that has the color blue and the shape circle, you want to get down to C. And the second one is how to learn the decision tree, which is going to be the key computational problem. So here is an example. You can just check that what I've done here is a good representation, right? So if you look at here, if everything that is red is in B, if you look at the green things, if the shape is square, it's in B. If the shape is circle, it's A, and so on. So the representation is the right representation, and we want to figure out eventually how to learn it. I want to make one request now that hopefully everyone is here. Please try to be here no later than 3 minutes after the beginning of the class, because it bothers me that a lot of people, at least 10, 15 people got in the last 5 minutes, and it bothers you, I think, too. So try to make, I promise that I will not start before 3 minutes after 12:30. Please be here by 12:33. Okay. So now let's continue. So I changed this representation a little bit because I want to simplify things. Instead of 3 labels, A, B, C, I'm going to deal now with 2 labels. Everything is going to be Boolean. It's going to be simple. Everything that we do with 3 categories, we can do with 2 and vice versa. It's just going to make our life a little bit simpler. But now what we have is a Boolean function, right? A function that maps to 0 and 1. And we can think about representation. I want to argue first that decision trees can represent any Boolean function. Why? The answer is here. I want to make sure that people understand. So we are all familiar with DNF representation, disjunctive normal form representations. If you're not, you have to refresh your memory. You want to be familiar with this. And you also want to know that this is a universal representation. Every Boolean function can be represented as a DNF. Why? Give me one sentence proof that pretty right. Let's make this a little bit more concise. Why can you represent any Boolean function as a DNF? What is a DNF? It's a bunch of conjunctions, x1 and x2 and x7, x9, and not x17. A bunch of conjunctions like this, and a disjunction between them, an OR between them. If I give you a Boolean function basically is a set of examples, n-dimensional examples, that are positive, and the rest are negative. So let's say I gave you all the positive example. I defined the Boolean function this way, right? How would you write it as a DNF? Yeah.
You see, you go through the truth table and see where the answer is positive, and that we see that what is the value of the variables. If they are, for example, 1, we create a conjunction of all that are 1 and not of all that are 0.
Exactly. So I take every example that is positive and I generate a full conjunction and dimensional conjunction from it by taking the conjunction of all the positive, those variables that are on, and the conjunction of the negation of the variables that are off. Right? So if the example is 1, 1, 0, 0, 0, I will do x1 and x2 and not x3 and not x4 and not x5. For each positive example, I generate this conjunction, and then I OR all of them. And I got a function that is positive if and only if the example is positive. So I have a DNF, and every Boolean function can be represented this way. So what you see here is that the same can be done for decision trees. Now, this is not necessarily the best or the smallest DNF to represent the function. Clearly, they are, in most cases, or in many cases, better representation, but at least it shows that it's a universal representation. The same holds for decision trees, right? I can also look at all the positive examples and define the path to the positive example, conjoin it, and I get a DNF, which means it's a universal representation too. From a learning perspective, is this good or bad? Basically, what I said is that I can represent any Boolean function, yeah?
It's too specific.
What do you mean too specific?
So you're enumerating every single body rather than making a general pattern.
Right. So basically, what you're saying, maybe it's too expressive. You can do everything you want, and maybe you will not be able to abstract from your data and generalize. So there could be some negative aspects of it. There are also positive aspects. You can express whatever you want, right? So you're not limited in terms of expressivity. But so far, what we know is that we can represent all Boolean functions. So the hypothesis space that we have, unlike what we had on Tuesday, where we had a very limited hypothesis space, only linear function in the feature space we use, here we have the space of all Boolean functions in the hypothesis space. Okay, in this specific thing, you can do your exercise and see that there are 2 to the 9 functions. Okay, so decision trees is going to be a collection of functions with discrete categories. As I said, I'm going to deal now with Boolean, but for the same price, you can do it for any set of categories and also real valued. We're going to talk about an algorithm that does it, and there's a family of algorithms that can learn decision trees. They're actually good algorithms, as you will see when you play with some in the next problem set. They are very efficient, in fact, in terms of processing large amounts of data. They're a little bit less efficient than other families of algorithms in terms of dealing with high-dimensional data. But of course, it becomes better and better. There are also ways to generalize these algorithms. We're going to talk a little bit about some generalization toward the end. For example, dealing with noisy data, dealing with missing attributes in the data, and so on. One way to think about it is essentially as splitting the space. So if my attributes are real valued, for example, I'm showing here 2 dimensions, y and x, you can think about these nodes as conditions, actually x is parallel conditions. X is less than 3, y is greater than 7, y is less than 5, and so on. And therefore, a decision tree basically splits this space into axis parallel rectangles and classify each rectangle separately. Right? So this would be perhaps sometimes a useful geometric interpretation. Okay, so what we know so far is that it can represent any Boolean function, can be viewed as a compact representation of the data. It's a very natural representation. You can think about it as kind of a 20-question game where you first ask a question about attribute 1, Depending on the answer, you go to attribute 2, and so on. And therefore, the evaluation of the decision tree is very easy, right? So if I have an example here, I ask, what is the value of outlook? Depending on the value, there are 3 options here. I go to one of these branches. If it happens to be overcast, I already know the label. If it's rain, I ask another question, and so on. So evaluation is very easy, and the question is how to learn. Now, of course, there's also the issue of given data, there could be multiple decision trees that can be used to represent this data. And the question is, what does it mean to be a good decision tree? Any idea, any suggestion? What's a good decision tree if you have multiple options? Yeah?
The simplest one that can classify.
The simplest one. How would you define simple?
The queue is like decision boundaries.
Perhaps the smallest number of nodes. Other suggestions? Yeah? Minimum length. Is it different than number of nodes? Another suggestion there?
For the height of the tree.
The height of the tree could also be a criterion. So how fast can you get to a leaf? Yeah? Okay, so that's, eventually that's going to be our goal. But the question is, as we learn, maybe we don't have access to this, so we want to have some goal, heuristics goal perhaps, of how to develop this tree. Okay, the problem, of course, okay. So I'm going to start with an example before I get to some of the problems that we have. And the example that we're going to play with is whether we're going to play tennis today or not. So here is the problem. We're going to have several features, 4 features. These are the values of the features. So outlook can be sun, overcast, rain. Temperature could be hot, mild, cool, and so on. And I'm going to have 2 labels, plus or minus. And this is the set of examples that I have, right? So I'm using some shortcuts that are defined here. 14 examples, outlook, temperature, humidity, wind. As you can see here, I have 5 negative examples, and the rest are positive. And the question is, how do we generate a decision tree? What would be an algorithm for a decision tree? Suggestions? Yeah?
You need to select the right attributes with every time. You have some criteria to say this is the best.
Okay, so the suggestion is choose an attribute. You have to have some criteria for how to choose an attribute, but let's assume I have a criteria to say this is the best attribute. Then I'm done, basically. Because once I've done this, I can recursively, I choose the attribute, I split based on the value of the attribute, and then I have the same problem multiple times. Okay? So that's a very simple algorithm, and this is, in fact, what we're going to do. So the data is going to be processed in batch. I have all the data to look at. And the algorithm, as suggested, is going to choose the best attribute and recursively develop the tree. Very simple. And I'm going to get something like this. So I chose outlook first, and then I look at all the examples for which outlook was sunny. 1, 2, 3, 4, 5 examples. And I only dealt with these and ran the same algorithm. And then I figured, okay, so now I want to choose humidity, and so on. So this is the algorithm, right? So just some notations. S is the set of the examples. Label is the label. Attributes, as I said, another name for features. And I'm running an algorithm that we call ID3, which is a heuristic, a very popular heuristic that was developed in the 60s, in fact. And I'm starting by asking whether all the examples are labeled the same. Otherwise, in this case, I just return the label. Nothing to do. Otherwise, I'm choosing an attribute. I'm choosing the best attribute. We'll have to define what do we mean by best. and how we choose it. But once we do it, for each possible value v of a, I'm adding a new tree branch, a equal v, and then I'm splitting my data set to several subsets that I call S of v, the subset of all the examples for which a is equal to v. If it's empty, I'm just adding one leaf node with the common value in this set, in S. Why do I need to do this? I can just leave it.
If you encounter a test example that has that attribute, but it's not in the training set, you need to be able to do something with that example.
Right. So exactly right. So what I need to do is I need to be able to build a structure that will behave, do something on all examples, not only those examples in the training. So I need to have these kind of escape routes for cases that I haven't seen. But this is, if I don't get this, I'm looking at this SV multiple times, multiple SV for different values of V, and I'm basically running the same algorithm for SV and for the new set of attributes. So I eliminated the attribute A, and I'm going to keep on going. Very simple algorithm. Okay, so now the question for us is, how do we choose best? And as you all suggested, our goal is really to find a small decision tree. The problem is, like many other problems, that really doing what we want is computationally hard. So computing the minimal decision tree that is consistent with the data is NP hard. So specifically, if I give you a data set and I tell you there exists a decision tree that is consistent with this data set, there could be multiple decisions. Finding the small one, and you can define small one in multiple ways. Let's define it as the one that has the minimal number of nodes. This problem is NP hard. So what we're going to do is not going to solve this problem exactly, but rather we're going to develop a greedy heuristic search algorithm that finds a simple tree, not necessarily the optimal tree, and it turns out to be a pretty good, empirically, pretty good algorithm that finds pretty good trees. Okay, so as we said, the main decision is the selection of the next attribute. So let's try to start with a simple example and see what is your suggestion for how to develop this heuristic. So here is a data set. I have examples with two features, A and B. They can be 0 or 1. I have 50 examples with 0, 0, 50, and they are negative. 50 examples that are negative with 0, 1. No examples with 1, 0, and 100 examples that are positive with 1, 1. What's your first attribute? Yeah? You want to split on A first. Why A?
Because if you split on A and out of the total 200 examples, you already get a best kind of split where your negatives and positives are separated.
Essentially, you already know what's going to happen once you split on A, right? So if I split on A, I get purely labeled node. I immediately know how to label it. It's a very simple tree, right? If A is 0, it's a negative example. If A is 1, it's a positive example. Clearly, that's what I want to do. If I did it on B, I wouldn't get such a simple tree, right? If B is 0, I know that it's negative, but if B is 1, I still have to ask another question. So in this case, it's a very easy decision. What if I'm going to change this data set? In the case of 1, 0, instead of 0 example, I now have 3 examples. What would you do now? Which is the best? Yeah.
So now we split on B because I know if B is 0, then it's minus, and then I have to look at both examples.
If B is 0, then it's minus, and
then on B, if B is 1, I still have to think about if A is 1 or not. So it doesn't matter which tree I choose.
What happens if A is 0?
Then it's still minus.
So in both cases, if the first answer is going to be 0, I know that it's a negative example, both in A and in B. So why would you prefer B over A?
I don't know. There's no reason I should do that.
Okay, but at least something to think about, yes?
If you split on A, then you
So you would choose A still. Okay, so that's a good way to think about it. So first of all, we all agree that in this case, the trees look structurally similar, right? So if I choose on B, as you said, if it's 0, I know. If it's 1, I still have to ask a question. If I choose on A, if it's 0, I know. If it's 1, I still need to ask a question. But once we put numbers here, as you suggest, if I choose A, I almost know everything, right? For half the data, I know. And for the second half, I almost know. I have very little uncertainty about what's going to be the label after the first question. On the other hand, here, if I get 0, I know for a quarter of the data. And I still don't really know what's going to happen here, right? I have a lot of uncertainty. So intuitively, I would go with the suggestion of choosing A, but we need to figure out a way to quantify things so that we can have an algorithm. So hopefully we can quantify this intuition, and in a few minutes you will have an algorithm that will choose A. So we want attributes that actually split the examples to sets that are relatively pure in one label. This is going to give us the shortest path, if you want, the quickest way to get to the leaves. And the heuristic that we're going to use is the most popular one. It's called information gain, that was developed, as I said, in the 60s by Quinlan. The key notion that we're going to introduce in order to do it is that of entropy, an information theory notion that is called entropy. So entropy is going to be defined for a set of examples or for a discrete distribution in the following way. So let's assume that I have data with two labels, positive and negative. Let P plus be the proportion of positive examples and P minus the proportion of negative examples. I'm going to define the entropy of this set as the minus P plus log P plus minus P minus log P minus. What does that mean? If you think a little bit about it, the two extremes are going to be, if all the examples belong to the same category, so P plus is 1 and P minus is 0, or vice versa, the entropy is going to be 0. Right? Both of these are going to be 0. If all the examples are equally mixed, so P plus equal to P minus equal to a half, then I'm going to get here log of a half. Think about it as log base 2. Easiest to think about it this way. And then I'm going to get a half, a 1 here. Everyone agrees with that? So I get 0 if I know the answer. Everything is positive or everything is negative. I get 1 if I have no idea what the answer is. It's completely uniform. So you can really think about entropy as the level of uncertainty that I have in the data. Again, here I have no uncertainty. I know exactly what the label is. Here I have maximum uncertainty. So we can generalize this definition to any discrete distribution or any split of a data set. If I have multiple labels, the entropy of the distribution over k labels, where P1 is the proportion of examples label 1, proportion of example label 2, proportion of examples label k. It's the negative sign of the sum P log P, Pi log Pi. Okay? Direct generalization. So let's look at some examples. And as I said, this comes from information theory, where the question is, how many bits do I need to encode a message that is drawn according to this distribution. But we actually don't need this insight. This is just for completeness. We can live with this insight of thinking about this as the level of uncertainty in the probability distribution. So here are some examples. Okay, so here I have, again, a distribution over two values, plus or minus. In this case, it's uniform. The entropy is 1. In this case, I almost know everything, right? Basically, almost all the data is positive. The entropy is going to be very low. And this is an intermediate case. I have more positive than negative, but it's about maybe a third, 2/3. Entropy is going to be somewhere in the middle. Let's look at another example where I have, let's say, 8 values. This is one case where I have one value that dominates over the others. This could be another case where I have a range of values, and this will be the uniform case. So what do you expect the entropy to be, let's say, on the left side? Somewhere in the middle, let's say. What about the right side? Relative to this, larger, smaller? More entropy, less entropy? Less entropy, because you basically know what's going to happen, right? So it's going to be small. What about the case in the middle? High entropy. What's going to be the entropy? Why 1? I don't know anything, so it's the maximal entropy. But before, when I showed 1, it was over 2 values. So I had a half log a half, which is a half. But here I have 8 values, so it's going to be 3, log 3. So just put the numbers in. I have an 8, log of an 8 in each component here, right? So it's a sum over an 8 times log of an 8. So the maximal value is going to be log number of values. But clearly the tendency is, once I don't know anything, the entropy is maximal. Once I know almost everything, the entropy is minimal. So really we want to think about high entropy as a high level of uncertainty, low entropy as no uncertainty, and that is going to drive the algorithm for decision tree. So I want to find this node, this attribute, that is going to do what? Yeah?
That when you split on that attribute, you get nodes such that the entropy is
I want to minimize entropy once I split on this node. I don't want to have uncertainty. I want to know what's going to happen, because this is going to mean that my route to the leaves is going to be the fastest. So that's what we want to do now, and now we're going to define it explicitly. So the notion is that of information gain. That is, let's assume that I start with a given set, and I know the entropy of this given set. I'm going to choose the node in such a way that it's going to maximize the information gain or minimize the entropy. Specifically, I'm going to define information gain for an attribute A as the expected reduction in the entropy that is caused by partitioning on this attribute. So I have a data set S, and I'm choosing A. The gain that I get from choosing A is, this is my starting point, the entropy of the data set, minus the average, the weighted average, over all possible values that A take, of the entropy of the remaining set. Right? So if I choose A, and it takes a value V, I'm computing the entropy of SV, and I'm weighing it by the size of SV relative to S, and I'm averaging. So the expected value of the reduction in the entropy that I got by choosing this attribute A. Again, SV is the subset of S where A takes the value V, and I'm computing 2 entropies. In fact, I will not care about this so much because this is going to be fixed for all A's. I will care about computing SV. So, and the idea is, as we said again, my goal is to get to low entropy which means I don't have a lot of uncertainty with respect to where the label is. Okay, so let's try some examples here. So this is, again, the data set that we have with these attributes, and I want to choose the best attribute. So what I'm going to do, I'm starting with this entropy. As I said, I have 9 or 5 examples that are negative, 9 that are positive. So my initial entropy is this, minus 9 over 14 log 9 over 14, 5 over 14 log 5 over 14. Now let's choose, if I choose Outlook, now I have to define 3 sets, because Outlook can be sunny, overcast, and rainy. For sunny, I have 5 examples. These are negative, and 2 of them are positive. So 2 over 5, 3 over 5. And the entropy of 2 over 5, 3 over 5 set is pretty high, right? I'm very close to uniform, close to 1. For overcast, all of them, all the 4 examples of overcast, 1, 2, 3, 4, all are positive. So I know immediately that the entropy is 0. For rainy, it's the same entropy. It's 3 over 5, 2 over 5. It doesn't matter what's positive, what's negative. And I also get a high entropy. So the expected entropy that I get is this average. 5 over 14 times this, 0 times this, and 5 over 14 here. This is the entropy that I got. And I have to do this computation for each one of the 4 attributes, right? So I choose an attribute, I look at the values that it can take, and the number of computation I have to do is the number of attributes, the number of values it can take. So I can do the same thing. Okay, so this is the information gain, right? So the difference between these. But really, so I care about maximizing the information gain. Let's see what happens. I can do the same thing for humidity. I'm not going to go over all the computation, but you can check if you want to make sure that you understand the definition. I'm going to get something else. This is going to be the expected entropy, and the information gain is going to be lower. And overall, that's what I get. Right? So I got 4 information gains, 1 for each of the attributes. And the largest one is Outlook. The largest one means the largest decrease in entropy. And I'm going to choose Outlook. I split on Outlook. And now I have 3 problems of the same type. I recurse on this. So these are the 3 problems that I have. The sunny one, the examples indices are here, just that you can check. 1, 2, 8, 9, 11 are the sunny examples. The split is 2 is plus, 3 is minus. And here I know immediately, as we knew when we computed the entropy, the same is for rain. And I need to continue until every attribute is included in the path, or there's nothing else to do. So for example, in this case, when I do it relative to sunny, I have to entertain humidity. Very easy to see that for humidity, if it's high, it's a negative example. If it's normal, it's a positive example. So it's going to be 0 times 3/5, 0 times 2/5. Right? I'm not going to gain anything. And the same, all these computations are very easy. The winner is going to be humidity, because I know basically what's going to happen. So I'm going to choose humidity here, and so on. Questions on this? So it's a very simple algorithm. Of course, I didn't prove anything. I didn't show you that this is the best thing to do, because it's not. But it's a very good thing to do with experiments of many, many years. And this is just a summary of the algorithm, right? So I want to induce decision trees. Basically, I ask some escape question at the beginning. Find the feature with the most information gain, which is the argmax over all xi's, where xi's are my attributes here. once I chose this argmax, this ith attribute, I'm adding children to this ith attribute. I'm defining the set for each one of the values that this ith attribute can take, and I recurse on this. Okay. Simple algorithm. No questions? Yeah.
So after we chose the outlook, then why did we look at sunny and we didn't, for example, look at rain?
Oh, we did.
Oh.
We looked at everything. I just gave the numbers for sunny. We have to do now.
So the second level doesn't have to be the same. I mean.
No, it's a recursive algorithm, right? So you have to do it for all the subtrees. So for overcast, we don't need to do it. Well, we need to do it, but it's immediately give us plus. And for rain, we have to do exactly the same thing that we did here. And once you do it, you will get this. You get that the best one is a win. So you can check and see what happens. Yeah.
What if the attributes take real number values? How do you?
Okay, so you can do exactly the same thing. Actually, you will also use ID3. The only thing that will matter is changes how you compute this function. The split is going to be.
How you define?
You'll have to discretize values. Yeah. So I'm going to give one example for how to discretize over attribute values, and similar principles are going to work also for regression trees that you can learn. I'm not going to talk about it because the algorithm is a little bit more complicated. But the principle is the same thing. You will, in fact, use an ID3 prime algorithm. So it's still going to be information gain based. You just compute it in a slightly more complicated way. Okay, but this actually brings us to an important question that will be probably the next slide. Just to summarize. So what we did is we ran a search algorithm on the space of decision trees, and we talked about pros and cons on this space, because the space is the space of all Boolean functions, which means any data set that you'll give me, I can actually learn a decision trees. Any data set that is labeled with positive and negative examples, I can learn a decision trees that represents it exactly, but, which is a good thing, but it's also a bad thing because I can fit any coincidental regularity that exists in the data and any noise that exists in the data. This is going to be what we're going to attend to in a couple of minutes. We also said that even though our goal is to find the best decision tree, we're not going to find the best because this problem is NP-hard. And what we did is essentially heuristic search without any backtracking. We just went down the tree and computed it. Now notice that it seems as if we are making statistically based decisions using all the data, right? Because we compute entropy at any point. Is it really using all the data? Yes, no? It's a binary question. You say no. Why not?
Because once we reach a point,
I think that what you say is right. I'm not sure I completely understood it. So here we definitely use all the data when we chose Outlook. When we chose Outlook, once we got to this branch of the tree, Outlook equal rain, we only use 5 examples, not all the data. Right? So as we go down the tree, is that what you said? Okay, so say it again.
what I'm saying is that, so after, okay, overcast that says yes, overcast category, other attributes are just ignored.
Okay, so you're looking at this branch and you say, if overcast if Outlook is overcast, I don't care about anything else. Yeah, so that's another way of saying that once you split, you disregard a lot of the data. You can also look at it in this branch. Once you know that Outlook is rain, further down decisions are going to depend only on a subset of the data. You will not touch all the data. Which means as you go down the decision tree, you make decision on less and less data. So if you want to think about statistical robustness of your decision, you become less and less robust because you make your splits based on less and less data. And this is something that you want to think about later on in terms of, do I really believe this tree? Or can I do something? Can I massage the tree a little bit so that the decisions are going to be more believable? And clearly, as you go down, the decisions are going to be less robust because you made them based on less data. So it's really not true that it's all data. At the beginning, it's all data. Later, it's not. OK, so we learned decision trees. And I want to talk about the quality or something about the quality of the decision tree that we got from the perspective of overfitting. We're going to address this also. So a little bit about history before we get to it. So the history of decision tree is like most of the learning algorithms that we're going to touch upon started many, many years ago in the 60s. In fact, was not developed by computer scientists, was developed by psychologists as a way to concisely represent data that has to do with concept learning. But the most popular heuristic that we are using was developed by Quinlan in the 70s. A group of statisticians, two of them became later very famous, wrote a book that is called CART, Classification and Regression Trees of Trees. And it's still a very, very good read that studies decision trees. There's been a lot of improvement. It was a very, very active research area in the 80s with a lot of improvements that I'm going to mention a few of them. You know, how to deal with continuous attributes, how to deal with missing data, how to deal with non-axis parallel splits. When I showed it before, I showed it as if all the splits are axis parallel. You can also do other things. But Quinlan actually had the most impact on this area, coming up with ID3 and then a few packages that suggested various or different variations of this in C4.5, C.5, and essentially all the commercial packages that you will look at or the open source are going to use these heuristics, Quinlan's heuristics. In terms of history, one thing that has made decision trees very popular is the realization that while you have an algorithm to learn a decision tree, perhaps a better way to use decision trees in many cases is not to learn one big decision tree, but rather to learn many decision trees and then to put them together in some ways. And I'm going to give an example later for one way of doing it, and you're going to play with it in the problem set also. Okay, so let's just move on to some generalization or some issues that come up with this. So here is one. I gave you a data set before, and the data set was used to represent we took all the 14 examples, represented them using this decision tree. Now someone actually gives us another example. Now it's sunny, hot, normal, strong, but it's no. If we try to classify this example, sunny, we don't care about hot, humidity is normal, it's yes. This is no, which means we need to add something to a tree to fit this data, right? I need to augment it by adding one more split. That the previous data that we had, the previous data set, did not force me to do. Good or bad? It's bad because I can always do it, right? It's a decision tree. It's very expressive. I can do, whenever you give me data, as long as the data is itself consistent, I can represent it. And this means that I can fit any noise or any coincidental regularity in the data, and I may not want to do it. So what I would like to do is I'd like to figure out how to trim the tree perhaps, or prune the tree so that I will not do this. And this is the notion of overfitting. So you can think about, this is the training data. It's a very sparse sample of the instance space. And you may not want to fit any noise in this data or regularity. You want to do something that is a little bit more robust. And the notion of overfitting is really important here. So how do we define overfitting? We're going to define it as hypothesis H is said to overfit the data if there is another hypothesis, H prime, such that H has smaller error than H prime on the training data, but larger error on the test data. So typically what you will see as you learn a decision tree is that you can improve the accuracy on training because you can completely fit your training data. But at some point, you really overfit some regularities, some coincidental regularities, or some noise in the training, and at some point, if you set aside some other data, the performance on this data might go down. This is where you want to stop. Right? So it's clear that this red curve is going to improve as the complexity of the trees grows, but you don't necessarily want to do it. Right? So you want to be able to maximize generalization. Many reasons for overfitting. Too much variance in the data. Really, I sampled a subset of the data, the instance space, but perhaps it so happened that the sample that I've taken is not a good representative of the data. This could happen. There's too much noise in the data. And you can think about multiple types of noise. You can think about attribute noise. When you look at the feature space, some of the features you didn't measure correctly. You can think about the label space. The example is correct, but the label actually should be negative. And when I measured it, it looked positive. So these are two types of noise, but they have the same impact on this learning. Really, in both cases, the reason we overfit is because we try always to minimize the empirical error, right? The error on the training data. And we can do it, right? Because it's a decision tree. And we may not, and this may not be the ideal thing to do. So what we're going to do in the context of decision trees is we're going to try to prune the decision tree. By pruning, we mean removing leaves and basically folding the tree up, assigning labels of the parents to all items underneath. You can prune the children of a node S if all the children are leaves, and the accuracy on the validation set, this is a new concept, doesn't decrease if we assign the most frequent last label to all the items in S. So I introduced this notion of validation set. So you have a training set. We talked about training set. We talked about test set. You typically also want to set aside a data set that we're going to call it development set or validation set that you're going to use typically to tweak parameters or help you pruning. And this is going to be something that will help you figure out, are we still making progress here? And in this case, it's going to guide your level of pruning. So really, there are two general approaches for pruning. One of them we call pre-pruning, which is as you learn, you decide at some point to stop growing the tree. And post-pruning is you grow the full tree and then go back and decide to fold some of the nodes. And there are several ways to decide what to prune or when to prune. Cross-validation, essentially the idea is that you set aside a data set and hold out set, and you evaluate utility. And there are a few other ways to do it, basically different kinds of statistical testing. We're going to talk a little bit about this. Essentially, you want to know whether the observed regularity is coincidental or not. And one way to do it is something that is called minimum description length, that kind of looks at whether the additional complexity of the hypothesis, sort of moving to a larger tree, is useful. Is it better to do this than just list all the exceptions to a small tree. All these things are related to a general notion that we're going to talk about later in the class, that was of regularizations. That is, we want to keep the hypothesis simple while maximizing its performance on the data, on the training data, but not necessarily learning the best hypothesis because of this trade-off. You can think about this also in the context of linear classifiers, not necessarily only in the context of trees. Also in the context of linear classifier, you can think about, I have data, I'm trying to fit a linear classifier that splits the data. Could you imagine a notion of simple here? All of them are linear classifiers. But
maximum of the weights are 0.
Say it again.
Maximum number of weights are 0.
Maximum number of weights in the weight vector is 0. Why is that simple?
You are not considering a lot of attributes. You are just looking at some important attributes.
Okay, so that's a way of defining simplicity. How would you think about this geometrically?
You are reducing the dimension.
Right, so you can reduce the dimensionality of the data and say, basically, now I have a lot less linear classifiers to consider if I'm reducing dimensionality, right? Because I have a lot less weight vectors to consider. That's one way to think about simplicity. Another way to think about simplicity in the space of linear classifiers. If my linear classifier, for example, has a thickness, so it's not a 0 thickness linear, but actually has some thickness, then I have a lot less linear classifiers that separates the data, right? Because they are thick. And it's harder to split the data with something that has thickness. Of course, the thicker it is, the harder it is to fit it. I have a lot less thick classifiers than classifier without thickness. So these are issues. In fact, these are very related, but not exactly the same notions of simplifying the hypothesis. But in all cases, we are kind of doing the same thing. We are playing a game that goes between trying to fit the training data, but not doing it with a very, very expressive function. So I'm going to take a small detour now for a few minutes and talk a little bit about generalization and overfitting. It's going to be a very hand-wavy description for now. Later on, we're going to be able to do this more mathematically and exact, but I'm going to start with it now. So, and in fact, finish this evening in the next lecture. So the notion that we have to remember is that we always think about learning when we analyze learning. This question came up last time, as there is a probability distribution over x, y, the instances, the labels, that governs the generation of the data. We don't know this probability distribution, but it exists and it governs the data that we see. What we assume, in most cases for the sake of analysis, is that the data that we see was drawn independently from this probability distribution. And this is a key assumption, typically doesn't hold, but allows us to analyze this. So each xy is drawn independently from this distribution. Okay, so we talked about overfitting. We said that a decision tree overfits the training data when its accuracy on the training data goes up, but its accuracy on the unseen data goes down. Why is this the right shape of the curves? I actually said this before. I just want to make sure that we're all in agreement. Yes?
I would actually expect, based on intuition, for the red curve to be flattened.
This one. Okay, let's start with the blue one. Why is the blue one like this? Yeah?
Because as you have more training data in, and then you put more branches down, so you're able to classify the training data more. So as the complexity increases, you're able to classify the training data.
Well, so it's as a function of the tree, of the size of the tree. As the tree grows, it can completely fit the data. And my accuracy is going to go up until it gets to 100%. Right? So the scenario I'm imagining here is someone sets aside a data set, a test set, or a validation set, or someone is an oracle that knows exactly what is the true error here. Right? So that's the scenario I'm imagining. And I'm looking at my algorithm, and whenever the algorithm, let's say I tell the algorithm, stop at this size, I've generated the decision tree, and I ask the oracle, what's the true error now? Right? So that's the scenario we're imagining when we're plotting this graph. So under this scenario, it makes sense that as you allow your algorithm to learn larger and larger trees, this oracle is going to give us better and better numbers in terms of performance on this whole distribution, the true error of the tree. Everyone agrees? Now to your question. So what's going to happen on test data? So is your complaint about this or about?
At the right-hand side, I would expect that if you have a very fine resolution line separating, let's say, two types of data, that if it's very fine resolution, maybe it doesn't really decrease accuracy, it just keeps it the same.
Okay, so first of all, don't take this too seriously. The key idea is that it's going to go down, and I think it will go down. And the reason it's going to go down is that what you're going to do is I gave you 100 examples to train on, right? If you learn a small tree on these 100 examples, you will learn a tree, and with some probability, you're going to do okay on some other examples that you have not seen. Once you completely fit the training data, so you learn the largest tree possible, and you completely fit your training data, you're less likely to actually do well on data that you haven't seen. This is a statistical thing. So your performance will actually go down until some point, and then there's nothing to say anymore. Yeah?
Is this because of the noise in the training data?
Because the training data is only a subset of the instance space. Even if it has no noise, you actually learn the function that knows how to do these 100 examples perfectly, but I don't know what it's going to do on other examples. It may not do well on other examples. Because I learned, so let's go to the DNF that I defined at the beginning of the class. You give me a Boolean function, and I'm going to define the following DNF. I'm going to take all the positive examples. For each positive example, I'm going to define a conjunction that is on for this example and off for all other examples. Right? That's easy to do. Everyone is with me? And then I'm going to define a DNF, which is just the union of all these positive examples. So this function is going to be positive only on your positive examples and negative elsewhere. This function is going to do perfectly well on this data that you gave me, is going to make mistakes on all other data sets. All other data sets. Do you agree? And this is exactly what we do when we grow the tree to exactly fit the data, the training data. It's going to make mistakes outside. So that's basically what this curve is supposed to intuit. Okay, I think we're going to stop now. What I'm going to do in the next lecture, which will be today at 7, is try to explain what's happening here, talk a little bit about experiments, and then move on to the next lecture where we're going to start talking about online learning. Okay, so see you in a few hours.